Finishing up this last example that we left off with in part 3, we've got the parametric equations. We found that there are in fact two tangent lines, and we found their slopes. Really 3 over radical 3 would be more simply written as radical 3. So you could even say that m would be plus or minus radical 3 in a simpler manner. But right now we'd like to take this a step further and find all points where there is a horizontal or a vertical tangent. And I've rewritten the derivative here in part B. Really what I hope that you know is that for a horizontal tangent, what has to happen is your numerator of your derivative must equal 0, while at the same time your denominator will not. If your numerator and denominator are both 0, that would require us to investigate that further, honestly through a L'Hopital type of an approach. But look, right here I've got this fraction though, and you can see very clearly that your top is going to be equal to 0. If you add a 3, divide by 3, you'd have t squared is equal to 1. And it won't take you all that long to solve to get t is equal to plus or minus 1. Checking when t is equal to plus or minus 1, you'll also see that your denominator would not be 0. So plugging in t equals 1 or t equals negative 1 makes the overall derivative 0. That's what we want to see happen, but we're asked to find points. Now the points in question, of course, are going to be ordered pairs. And in all honesty, just come right back up here to our x and to our y. And if you were to plug in a 1, we can say that there are horizontal tangents at an x value of, well, 1 squared. If you were to plug in a 1, you'd get 1 to the third for y, minus 3 times 1. Well, that's 1 minus 3, you'd get negative 2. And also, if you plugged in negative 1, your x value of t squared, negative 1 squared, is still a 1. But here things get a little bit different. Plugging in negative 1, you'd get negative 1 to the third, minus 3 times negative 1. You'd really have negative 1 plus a 3. That would be a 2. So you've got horizontal tangents at these two locations. By way of comparison, if you were to take a look at your vertical tangent line, a vertical tangent will occur where your denominator is equal to 0, and at the same time your numerator is not 0. Divide by 2, you'd see t is equal to 0 itself, and if you were to plug in 0 to the top, you would just get negative 3. So sure enough, plugging in t equals 0, your derivative is, undefined. So what you'd like to see is that your vertical tangent is going to occur at a specific point, at a particular x comma y. But if you were to come back up here, you can see if you were to plug in 0 for your for your t value, 0 squared, 0 for your t right here, you would quickly get 0 comma 0. X and y are both going to be 0, so we're pretty much done right there. Okay, so one last final thing and then we're through. Arc length. For any of these curves, if you wanted to find the arc length for a given t value that would start and an ending t value, as long as dx dt and dy dt are continuous functions, this integral, integrating from t equals 1 to t, or t1 up to t2, of the square root of dx dt squared plus dy dt squared with respect to dt, this will give it to you. So just want to quickly finish this thing up. Let's find what our dx dt is. Dx dt, if I gave you cosine of t, raising that up to the third, you'd get 3, and then you'd have of course you'd bring down the 3, you'd get cosine of t squared, but the derivative of cosine is negative sine of t. Remember the chain rule. And your dx dt would then be negative 3 sine of t cosine of t whole quantity squared. dy dt is a little bit easier to work out. If y is equal to sine of t, raise that up to the third power. Bring down that third when you take your derivative. You'll have 3 sine of t squared. But the derivative of sine is cosine. So this works out a little bit nicer. We get dy dt is 3 cosine of t. Then we have sine of t whole thing squared. We're integrating between 0 and 2 pi. So the arc length will just go between 0 and 2 pi of, well, now I need dx dt squared, so I'd go negative 3 sine of t cosine of t squared, and then you'd have to square that, plus dy dt, that's 3 cosine of t sine of t whole thing squared, and then we'd have dt. Many kids feel quite comfortable typing that in. And that's fine. By the way, the answer you would get would be a 6. You could check that out. I did talk in class about a nice, clever way that we could deal with this and make life a little bit simpler. What you can do is get x1t and y1t to be these derivatives. What I did is I went back to y and I typed in x1t. I just retyped this negative 3 sine t in parentheses cosine of t squared. Then I also could type in for dy dt, put that into y1t. Just type in 3 cosine of t sine of t squared. Why did I do that? Well, you're going to have to type it out anyway at some point, and you could put it in here. It might seem a little strange to do that. But what you can then do is more or less just type that formula out and get your answer to be 6. I'll do that real quickly from the start. We'll go to fn and we'll go from 0, get up here is 2, and then we'll bring in a pi. Of course, we'll type in the square root, but you might wonder, where's x1t? Well, it's vars. Hit the right arrow to y vars. This time go to parametric, and you can get x1t, and then you can just hit squared, plus, now you can get y1t, hit vars, right arrow to y vars, down to parametric, bring it right down here. Whether you're typing it out directly or in this manner, you're going to get the same answer. This would just allow you to maybe not deal with the parentheses as much. It's going to take a little while to work this thing out, but like I said, eventually you'll get an answer of 6. Know this formula because when we study vectors, we're going to see it yet again.